we started kind of beyond homogeneous, beyond isotropic homogeneous linear elasticity topics with anisotropic elasticity. And we talked about these different notations, Voigt notations, which is kind of a contracted form. And we talked about two cases of symmetry. One when you have a plane of symmetry, and the second one when you have three mutually perpendicular planes of symmetry. And we talked about implications that some of the materials that you work with actually possess this kind of symmetry. So the next one, we have two more cases to look into. And the next one is when we have an axis of symmetry. And this is also a very important case. So I'm adding this to the same notes, and then I put the notes on Canvas, all of that for this topic. So case 4 is case 3, I'm sorry. Case what happened from the beginning? Okay, I don't know what happened. Let me get this restarted. So case 3 is about having an axis of symmetry. What is... I don't know what is happening today. Axis of symmetry. So what does it mean? It means that if you rotate, so we actually say axis of symmetry of order n. Let me just write this first, and then I explain what this is. And that means that if you rotate the material, the macrostructure, by an angle which is 2 pi over n, everything stays the same. So that is being invariant with respect to rotation about this axis of an angle 2 pi over n. So let's write it. So elastic moduli remain the same for rotations of 2 pi over n about the axis of symmetry. So now, with this definition, if we have symmetry with respect to a plane, what would be n? When you have a plane of symmetry, exactly, n would be 2. I'm having a hard time, so I'm going to change the battery because sometimes this works. Are the new ones also, the stylus needs to be changed, the battery very soon? Or? Just one. No? So. Hopefully this is going to, that's why I always carry extra battery with me. So if n is equal to 2, this would be exactly like plane of symmetry. So let's see if this is helping. So So it turns out that actually the only types of symmetry of this type that can exist are for n equal to 2, 3, 4, 6, and infinity. Now, infinity here means that for any rotation about that axis, the material, the elastic moduli stay the same. So I would define it as symmetry for arbitrary rotations about the axis. So from your previous experience, do you remember how would you call this type of material where you have one axis of symmetry and no matter which direction you look at, everything stays the same. So no matter how much you rotate, you're going to see the same properties. How would we call this kind of material?
Transverse case.
Exactly. So this is what you may have seen as transversely isotropic. Because in one direction, things are different from all the other directions. So if you have, let's say, if this is the axis of symmetry, no matter where you look at around you, everything is the same. So in that direction, everything is isotropic. The only difference is this direction versus the direction which is perpendicular. Now, could you think of a material or a situation where this kind of anisotropy is basically very common? I'm looking at Clay because this is kind of what he has to answer. Exactly. In the earth, this is something which is common. So because of the pressure that the material above every point inside in the subsurface exerts, in the vertical direction, in the depth direction, everything is different. But if you look around in the horizontal direction, pretty much you can assume that you have isotropy. Does it make sense? Now, last time, do you remember how we developed the elastic tensors? We looked at Q, and then we said, okay, under these rotations, the elastic tensor should be invariant. So for rotation, the Q is, of course, not as simple. So we have cosine theta, sine theta, 0. So if we get the z-axis be the rotation, the axis of symmetry, I should say that. So if you rotate around z, then z doesn't change, but then you have this q. Now, if you do what we did before, you get the elastic tensor for this kind of material. So it's very, very important. So if you remember, we went from 21 constants to 13, right? And then how many? To 9. Now we want to see to how many do we go? Do you remember to how many? 5. Exactly. So let's look at how it would look like for this case. I was drawing all of them in a different. Here, this one will be a little bit hard to. The ones which are 0 will be 0. I have to write it, I think. So let's then continue and write it here. So it looks something like that, the elastic tensor in this case. So we have C1111, C1122, C1133, and these are 0. And then we have C1111, C1133, and here is 0. And then we have C3333, 0. I'm sorry, what?
The diagonal should be 2222 in the middle one.
No.
Oh, is this?
No, it's not.
Oh,
So it's about the symmetry. So that's why 1 and 2 are actually the same. So that's why it doesn't become. So the number of components are the same as before, but they are not independent. We'll count now. The number of independent elastic constants is only 5. So then you have C2323. That's why I wasn't able to use what we had before. C2323 still. And this last one is 1/2 C1111 minus C1122. So we have 1, 2, 3, 4, and 5 independent constants. But the others are not 0. They depend on each other because you have basically two perpendicular directions where things are the same. So I already told you that from 21 we go to 5. And by that I mean independent constants. And case 4 is complete symmetry, also known as exactly. This is what you have seen before, where now the way that we looked at this before was this way. We have the Lame's constants, lambda and mu. This is the notation you have seen before. If you remember, this was also a part of a homework very early on. And then if you use the engineering Voigt notation, then again the number of non-zero components don't change. What changes is that you are going to have dependency between the constants. So everything will be just and of course and in this case 21 is reduced to 2. Okay. So in our discussion about what else is there beyond what you have seen in linear elasticity, I add a few things also on non-homogeneous elasticity. So, any questions about anisotropy so far? So far, this is 14a. So what does it mean, non-homogeneous, and who cares about that? And I told you that it's very important to distinguish these two things from each other. Again, what does it mean? How would you define it? In elasticity. What is, not in general. What is a non-homogeneous elasticity? What is a non-homogeneous elastic material? What makes a material non-homogeneous? Gerald?
It depends, the response depends spatially.
Exactly, that's a really nice response. So the deformation response or the elastic properties are different spatially. So that's kind of what I was looking for. And from our discussion last time, what do you expect? Where does it come from? Where does anisotropy come from? It comes from microstructure. So if the microstructure has variability, especially, then you expect to have also variability, especially in elastic properties. So let's just write it. So later on, if you wanted to look at it to remember, so materials have a spatially varying microstructure, which would translate into a spatial variation in elastic properties. Now, examples. Why do we care about that? And then try to give me some examples from nature first. Do you know any material which would have a different property if you sample it from there or if you sample it from here? That's what it means.
Tree is a good example.
I'm sorry.
A tree.
Wood?
Yeah, wood. Like the bark has different properties in the bulk, or you could do the same thing with bones.
Exactly, bones, trees. These are all good examples. Generally, a lot of biological materials, because through the evolution, the places where you are getting more stress, it has developed differently than, let's say, organs where you don't have as much stress. So because of that, like bones, for example, or bones are very anisotropic. When we talked about anisotropy, I didn't mention it, I forgot. But these are good examples. Geomaterials, they can be very heterogeneous. So those are the examples from nature: wood, bone, geomaterials. Now, can you think about reasons that you want to actually build material? So have you heard about this? You want to actually build in heterogeneity inside the material. Yes?
Kind of do like a thermal conductor or some sort of thermal system. Then on the outside to be insulated with the inside to be able to thermal conductor kind of keep around.
Exactly. In that case, you try to build in some sort of gradation inside the material. And these are sometimes called like functionally graded materials, but now the buzzword for these are metamaterials. So when you think about, and it's really a booming field. And why is it a booming field? I know some of you are working in additive manufacturing. So in additive manufacturing, you can control how you build a part. So if you can think about changing the material properties continuously such that you have some exotic properties, now it is very possible to actually build them. So you can basically build in this gradation into the material to do different things. Like in my area, there are acoustic metamaterials, so you can grade the properties of the material such that it has very unique capability. For example, you can have some materials that if you put it around a space, not a spaceship, like a submarine, for example, it would be visible to sonar, invisible to sonar. And you can imagine what the implications of that are, right? So actually, this is one of the first applications of acoustic metamaterials. So you can build your submarine from material that if someone tries to find your submarine and is using sonar, which if you're not familiar are acoustic waves, they would never see your submarine. It behaves as if it is not there. That's cool, right? Or for example, one of my students just finished her thesis. So what we are doing is you can change the material such that it attenuates the waves, which can be very useful for shock absorbance, can be very useful for protection against vibration, etc. So you want to build in heterogeneity into your material consciously, intentionally. So because of that, this is also important. A lot of times you would use numerical simulations, but if you know how to deal with the problem analytically, sometimes you can get very simple analytical expressions, because a lot of times for metamaterials you want to vary things continuously. Like you decide what you want to do and then you see what the implications are. Well, I hope you are a little bit inspired about that, because this is kind of a cool new area of research in my point of view. So a lot of times for this structured metamaterial, if I use like CIJ, the worked, you actually have simple dependence on a special coordinate x, for example. It can be linear, like this. It can be exponential, etc. And because of that, sometimes it's important to understand how it's actually affecting the properties. And more importantly, it's important that you always distinguish the anisotropy from heterogeneity. So, well, how does it change the elasticity problems if you want to solve a material which has heterogeneity? On a very high level, I just give you some ideas what will happen if you have that. So what happens is that everything else stays the same. But when you write the Hooke's law, so you remember those 15 equations, field equations of elasticity, we repeated these so many times that I'm sure you have some mental image of that. So if you want to write it, before it looked like this, And now, basically that constant is not constant anymore, would depend on the spatial coordinate x. So everything else stays the same. The implications of this is that, for example, if you want to develop, maybe I write that other field equations and I'm talking about those first ones, not what we developed afterwards. Because if you remember what we did in later stages in displacement or stress formulation, we got the Hooke's law, we substituted it, and then we developed Navier equation or Beltrami-Miche. You cannot do that so easily anymore if your Hooke's law is different. But the field equations, the equilibrium, the strain compatibility, those won't change. Those will have the same form. Other field equations stay the same. So just to give you a taste of how things would look like, if you want to then develop displacement formulation, for example, displacement formulation and we, just for simplicity, with no body forces, the Cauchy law was like this, right? So if this is equal to 0, we only have that. Now, if you want to, if your material is not homogeneous anymore, it will look like this. Now I write it this way for clarity. Then you have Cij KL, because this is with respect to the spatial coordinate J. And then the strain, you can use the relationship between a strain and displacement. You can and at some point I told you I want everyone, like, you always remember this equation, right? Right? So if you write that, because of the symmetry of the strain tensor, this will be reduced to right? I wish we had a space. Maybe I write it. You all know that, so I don't need to keep it. So I write this here. Question? And then if you expand that, what do you get? So now before, you would take the elastic constant out of this derivative. Now you can't do it anymore. So then you get Ij, Cij, KL. So the first one comes out, UK, Lj, and then you will have another term so this is exactly, if we only had that, we would get the Navier equation. But then you have an extra term. I'm sorry. So the difference here is that C is not constant. So if C is a function of X, like this, if you take the derivative with respect to xj, then you cannot take it just simply out. Right? So it will look like that. So you will have this extra term because of heterogeneity. Now, as you may guess, everything becomes very complicated. Just to give you a taste, I'm not going to go through it. Just to see how it looks like, I just write one set of equation. If you assume that everything is isotropic, so you have and then if you look at the two-dimensional calculations for formulation for plane strain, so in that case, if it is isotropic, we only have two constants, right? Lames constant, lambda and mu. But then they are not constant anymore. They are going to be a function of x and y. If the material is heterogeneous. And in that case, the formulation, for example, in displacement formulation would look something like that. I just write one equation so that you see how complicated things will become if these constants are not real constants. Derivative of mu with respect to x so you are going to have terms which are the derivatives of Lame constants with respect to x and y. And of course, if you set those equal to 0, I hope you see the form of Navier equation for plane strain. And if you want to see the form of other equations, you can look at chapter 14 in the book. I'm not going to write the equations in. I just wanted to give you kind of a taste of how things will look like. And that you never would mix up heterogeneity and anisotropy. These are really different things. So you can have isotropy, but heterogeneity. Yes?
So in the discrete case, like a really common example is, there's two materials with different thicknesses, but they have a temperature. You plot them as because they have different thicknesses, they want to displace certain amounts. And you get a strain of heat, or a stress of heat interface.
Yeah.
Do you get the same thing here discontinuous, or does that discontinuous get rid of that interface stress?
There you have two material and then you have contact. This is different. This is like one material where things are continuously changing inside. Does it make sense?
So if you had the long extract and you had the change in the stiffness value, at one value of x, one stiffness, and another value of x, another stiffness, when the displacement still want to, I guess what I'm asking is the fact that it's continuous get rid of that problem.
If you set the boundary, if the boundary conditions are supposed to be, so you're saying that you have two materials with an interface, and one of them, let's say, the modulus is a function of x.
Yeah.
And then you are, and they have different thermal coefficients, thermal expansion coefficients.
Yeah, that's fine.
Okay. And then what is the question?
So my question is, in the discrete case, you just have two materials. If you apply a temperature, you get the difference in the amount of displacement or what they want to displace. They're perfectly bonded via the stress interface. So
Right.
my question is, do we see something similar here in the continuous case, or is the fact that it's continuous get rid of that interface stress?
You are going to still have stress at the interface, but the distribution will be different depending on the distribution that you have here for elastic modulus.
Right.
If it is, yes.
Sorry, slightly different question instead. So,
Let's not talk about thermal stresses because we didn't talk about it yet. Let's talk about mechanical stresses. So the boundary condition is still perfectly bounded.
yeah, so I guess my question is, this is large scale, but if you shrink this down and maybe if you made a bunch of blocks on top of each other and each one had a slightly different elastic modulus and then you shrunk everything down, that's essentially the continuous case.
Right.
So in the discrete case, at large scale, we have this effect. You have sometimes interface stress because the two materials want to act differently. Here, when it's really, really tiny, does the fact that it's continuous get rid of that interface stress, or you still get something?
Okay, now I understand what you're asking. So you're kind of want to say if you zoom in into your material, what is happening? Because it is continuous, you're not going to have internal stresses. Right? Yes.
Essentially, the homogeneity is based on microscale.
Exactly.
But this interface is not based on microscale. But they are different materials. So the interface, you are not able to reduce it to micro level, can you?
No, if I understand that correctly, he's saying that if you have something which has a gradient, let's say just look at this is the, and then if you want to take a small piece of it, since things are changing, what's happening there? If it is really continuous, you should not get like internal stresses because of that, because you have continuity. I mean, at least at micro level. But the distribution will be different. So the stress distribution will be different. If I knew that you guys are interested in, I thought there was an example we could have solved in the class. I just wasn't sure how much interest there would be. What happened?
These have like a quiz.
No. I don't think this quiz is just to see if you are following and if you are not overwhelmed with other things you have to do. No. It's more like if this is something that you are going to use it in your research, if you have seen something similar that you know where to go, I look at things differently. I know you guys are concerned about other things. Yeah. Okay. So you see that there are equations. So if you have here like really an expression for Lammers constants, you can put it there, and it will be you solve the continuous equation. So you at the end you are going to get continuous a field at the end, but it will look different. So the example was to show you how things can be different. Sometimes it can be a little bit different, sometimes it can be a lot different if you have heterogeneity. So I don't think there is any need, but for example, if you look in the book, the biharmonic equation looks very, very complicated as well. In a lot of these applications, people tend to assume that Poisson's ratio doesn't have such a big effect. So you kind of ignore the changes in Poisson's ratio because people have seen in experiments that Poisson's ratio effect doesn't affect the deformation as much. So sometimes they just play with one parameter like elastic modulus, etc. Anyway, this is just to give you some ideas that, the things which are possible. And then in our departure from linear elasticity, I promised you, probably you don't remember, that we do some nonlinear elasticity. So This is something close to my heart because this is related to some of the research I'm doing. For talking about nonlinear elasticity, I need to step back a little bit and remind you about where we set ourselves to have everything linear. And I try to be fast in doing that, but it's important, this part, a lot. I know that some of you do research related to nonlinear elasticity or even nonlinear inelasticity. So this is important. If you remember, when we were looking at the, and this is not in the book, but I've uploaded for you a chapter of the book, which if you are interested, you can look further in that. So if you remember, we did something like this in very long time ago. We looked at a very small element, and I assumed that this element was a square for no real good reason other than that it is simple. And we said that a strain is change in length or angle, and you have this in your notes, and I'm just drawing as much as I need to kind of set the stage to give you some information or some taste of nonlinear elasticity without going to too much details. But also to show you the utility of some of the things you have learned in this class. So we took one small element and we looked at the deformation and the displacement. We said, okay, if you write the displacement at point xp as a Taylor expansion around point xa, then you have a linear term, which we discussed this in length. This would be the gradient of the displacement, which is linear in delta x1. And then we talked about these higher order terms. And to make everything easy and to start linear elasticity, I told you that the gradient of displacement has to be a small, and if it is a small, we can assume that these higher order terms are 0. So nonlinearity comes into play when the gradient of displacement cannot be assumed to be so small, equal to 0. Meaning that the changes, is this rain? And I bike home. I have poncho and everything over. So then when these higher order terms are not equal to 0, then we are going to have nonlinearity. And then I have to also remind you that when we assume that this is the case, we could very easily say, okay, uxp minus ux1 is delta x1 prime, and this is equal to delta x1 and plus, you remember some things like that from long time ago? And from here, we found out that the gradient of the displacement can be written as the summation of two tensors, one symmetric, one skew symmetric or antisymmetric. And then what did we find about this skew symmetric part? I'm sorry? Yes, but what does it mean, please? Not rotation, infinitesimal rotation. That word is important because if the higher order terms are not equal to 0, none of these things are valid. And anyway, here we learned that Eij is what is the relationship between displacement and a strain? So the symmetric part is the strain tensor, and also at some point we talked about a strain energy density. And this is the area under the strain stress curve. So this is what is a strain energy density. It is the strain energy per unit volume, right? I know I'm going a little bit too fast, but it's because this we have seen before. And if everything is linear elastic, if a stress-strain relationship is linear, so here the area under the curve is just 1/2 sigma times E, which you can write using Hooke's law. Now everything is linear elastic. Like this. And the last thing that I want to recall is that using the same relationship, a stress is a derivative of the strain energy density with respect to a strain. You have all seen this before in this class. Now, why I'm saying these things, I want you to remember a few things. This is all linear elasticity. Now, when material is linear elastic, when we say linear is always a relationship between two things. We said it's linear in gradient of displacement. What is the order of a strain energy density in a strain? You can see it. It's also of second order. So the material is linear elastic, which is linear. The strain energy is of second order in a strain. Okay, so let's write this. So the linear elastic constants sometimes are called, because of that, the second order elastic constants, which may look a little bit strange to you because you always think about linear and you don't think about second order, you think about first order, but that's the reason. So if the material is linear elastic, the energy is actually of second order. So a lot of times people would say second order elastic constants. Those are Lamé constants. Now why I'm saying this, now let's imagine that the strains are not so small. So we are not looking at very, very large strains like the ones Tom is probably looking at in his research. We are looking at what I would call weakly nonlinear materials. This is giving me a hard time today for some reason. So, weakly nonlinear material, and they're elastic still. Weakly because it's not that nonlinear. So nonlinearity can come from the material behavior. The material can be nonlinear. Also, if the deformation is a lot, the geometry can cause nonlinearity. The weakly nonlinear materials, the geometry is not changing as much. So that part is not being included there. Now, if we look at the strain energy density for a weakly nonlinear material, we need to look at a little bit higher order terms. So I already told you that for linear elastic materials, the strain energy density looks like this. Now I use E. I will explain to you why for a strain. And if you want to just have a little bit of nonlinearity, instead of just this, we need to take into account higher order terms in a strain. And this is how it would look like. Then you have elastic tensor of 6th order and Eij, EKL, EMN. So far, because we were looking at linear elastic materials, the reference coordinates and the material coordinates were the same. At some point I told you we don't differentiate between the two. But when you look at the nonlinear materials, you have to differentiate the two. And typically for weakly nonlinear materials, we use the reference coordinate. So this is called Lagrangian way of formulating the elastic equations. And normally is any of you work with fluids? Great. So we don't have anyone who opposes that, because people who do research in fluid mechanics, they actually always travel with the fluid. And that would be an Eulerian formulation. So that's why I use here E to emphasize that this is a Lagrangian strain tensor. So E is symmetric. And just like before, when we had Cijk L, I told you that we can use Voigt notation and reduce it to Ij. If you are looking at the 6th order elastic tensor IJKLMN, it turns out that this can also be reduced because of the symmetry of the strain tensor to Cijk. Sometimes you see that. And just like before, Ijk range from 1 to, making sure you are awake, I and J range from 1 to 6. pay attention that the strain energy, now the order in a strain for this nonlinearity is of third order. Okay. Because of that, sometimes these are called third order elastic constants. Yes. Yes, but this is related to the material properties. So almost all the materials start with the linear, most of the materials, and then now it's true that it's because you're approaching this region, but how far and how it bends depends on the material. Simple. Yes.
Can we see that from
No, so here this nonlinearity, the way I'm formulating it, is still very weak. It does not take into account really, it's not as much as, it doesn't take into account geometric nonlinearity. I don't know what exactly, I mean, are you asking that if you draw it, you can get it, or?
Yeah, there are some geometric nonlinearity. It's not true problems.
No, this is not a very strong nonlinearity. This is not because, you know, the geometry is going to change that much. But you cannot ignore the changes anymore. So the things that we ignored when I was developing these equations, if you go back, here you don't say that. You say to the one order higher, you retain everything. You still are getting rid of the rest. Does it make sense? I'm just trying to give you a snapshot of things without hopefully not making you confused. So this is third order elastic constants. So now these so we learned that the second, and that's why sometimes this is called second order. Which is a little bit strange because you think those are linear, have to be first order, but now you know. We already know this. CIJKL. And one way to write it is introducing this symbol, which is just 1/2 of delta IK, delta JL plus delta IL, delta JK. Maybe I should have told you like where this is very important, or at least to me. This is when, for example, if you're looking at waves which have amplitudes which are larger than, let's say 10, which cause strains larger than 10 to the -6. So things are still very small, but they're large enough such that you cannot just ignore the other terms. Because if the strain is very, very small, if you 3 times multiply, it becomes very, very small. Right? So this is, for example, that's where it has one application that I'm interested in, or it's related to my research. So still things are not that bad. And so this is what we know. Now, how about this 6th order elastic tensor? So one way to formulate this is using these letters A, B, and C. Maybe I write this here. Plus 2B delta Ij I K element plus delta KL I Ij delta M I Ij KL plus A over 2 delta Ik I J L M N plus delta I L I J K M N plus delta J K I L M N plus delta J L I K M N 2C delta I J K L M N delta I J K L M N M N I J. I'm just checking. So I hope that you appreciate that using the index notation you can actually write things nicely here. And this A, B, and C, so we have here lambda and mu, and then you have this C, B, and A. So lambda and mu, of course, are Lamé constants. Again, I want you to know, if you see somewhere second order, why it is called second order elastic constants, because everything we are assuming now homogeneous, etc. And then A, B, and C are called, and these are normally just, we know them as third order elastic constants. So and there is another very famous, so if this is something that you would either ever deal with, you may hear this name Monaghan, and he is using different notation. He uses L, M, and N instead of B, A, B, and C, and the relationship between the two is like this. There are other notations too, but these are the most common ones. So this means that if you have isotropy, homogeneous, now if you have weakly nonlinear material, you need, other than the two, you need 3 more elastic constants. And it turns out that, this is not what I made up because this is related to my research, the best way to measure these elastic constants is using ultrasonic testing. So what people do is you load very gently the material and then you measure the velocity of waves with different polarization. Polarization means particle displacement. So you are loading the material, you measure different velocities in different directions, and actually you can use them to get ABC or LMN. And then you characterize your material to a higher order in terms of nonlinearity. And of course, this is not valid if you are dealing with shock loads where the load rate is very high. So that induces almost always inelasticity, so you have to deal with plasticity. So you need to take some other courses which deal with plasticity, and then geometrical nonlinearity and all those complications that comes with it. So Any questions? I hope this gave you a little bit of a taste of, how things look like if we go a little bit higher. So now